All right, so in this video, we're going to take a look at a couple examples dealing with substitutions in multiple integrals. This first one, we're going to find the area in quadrant 1 bounded by the 4 curves given on the screen. And so to get this thing started, it's probably best just to take a look and see what we're dealing with geometrically to make the connection a little bit more clear. So if we say that this is the xy plane, we've got y equals x squared. That looks something like this. We've got y equals 4x squared, or excuse me, 2x squared. That looks something like that. We've got our x equals y squared right here. And then we've got our x equals 4y squared right there. So this whole thing that we're trying to find the area of sits right in there. So bounded by all 4 of those. And you've done enough of these setups by now to know that would be a pretty complicated setup and a lot of unnecessary work if you are actually having to integrate it out. So we're going to make a substitution. Now, the first thing is to just kind of notice the similarities between what you're given right here. And so for this first one, I might recognize this as maybe a y over x squared equaling 1. And this one over here is y over x squared equaling 2. So that tells me that maybe I should come down here and say, let's let u equal y over x squared. If I do that, then u is going to equal 1 and u is going to equal 2. And those are going to be much easier numbers to deal with. In a similar way, down here we could say x over y squared equals 1 and x over y squared equals 4. Therefore, maybe my next substitution would be v equals x over y squared, meaning that v is going to be equal to 1 and v is going to be equal to 4. So again, these things here were just me manipulating this to come up with our nice new region. And that new region in the UV plane would be from 1 to 2 on the u-axis and 1 to 4 on the v-axis. So much like the last example, we're looking pretty nice here dealing with some rectangle with all constants. So now, the next thing we're going to do is we're going to need to find the x of u. Maybe I'll write it here so you guys can see it better. We're going to need x of uv and y of uv. So I'm going to need my functions now with respect to u's and v's. So if I take a look at these two things that I started with, the first thing you'll see pretty easily is that y can equal ux squared, and from that second one, this one here, the x can equal vy squared. So now it's just a matter of essentially making substitutions until you get both of these in terms of u's and v's. So what I'll do is I'll take the x, being this guy, and I'll plug that in right there. I'll take the y, being this guy, and plug that in right there. So we'll have a y equals u, and then a v squared y to the 4th, and then an x, which is going to be a v u squared x to the 4th. Now, simplifying it down a little bit, we've got a y cubed over here, if I divide, equals the 1 over uv squared. Similarly, we've got an x cubed equals 1 over vu squared. And then get y all by itself, I'll go ahead and take the cube root of everything, which leaves us with 1 over u to the 1/3, v to the 2/3, and then x equals 1 over v to the 1/3, u to the 2/3. So these are going to be now what I have to substitute in for x's and y's. Now, in this particular case, we're computing area, so there's not actually going to be that additional function there that I have to substitute in, but these values are going to come into play now when we compute the Jacobian. So, for the Jacobian, j of uv, I'm going to start here with the partial x, partial u. So the partial derivative of x with respect to u, and that's going to be a negative 2 over 3u to the 5/3 v to the 1/3 The next one would be the partial of x with respect to v. So it's partial of x with respect to v. That's going to be our -1 over 3 u to the 2/3 v to the 4/3. And feel free to pause the video if you need to run through those derivatives on your own. If you manipulate these by just putting the variable, if you will, up top, maybe with a negative exponent, then it's just a matter of multiplying down and subtracting, which is what I've done on both of these. So then down here we've got the partial of y with respect to u, partial derivative of y with respect to v. So this one's going to be a -1 over 3u to the 4/3, v to the 2/3, and then a -2 over 3u to the 1/3, v to the 5/3. Now this is just your basic 2 by 2 determinant, so we're going to multiply these two together minus the product of these two things, and it's actually pretty nice how it comes out. This comes out to be 1 over 3 u squared v squared. Alright, so now we're ready to put it all together. The area is going to be that double integral. And again, it's an area double integral, so no function there. The only thing we'll need is the Jacobian, or the distortion factor, which would be a 1 over 3 u squared v squared. Now we've got some combination of du and dv. Since they're all constants, it really doesn't matter. I'll go du dv, and if that's the order I go, then my u's would range from 1 to 2, and my v's would range from 1 to 4. So this would be our setup and our computation for area, which you could see would be a whole lot easier than having to deal with this region up here.